Assalamualaikum and hi everyone. Today we are going to present our assignment video which is relativistic momentum. So my name is Mohd Sufian bin Jalil from AS2513D2 and my partner is Aniq Fakhrullah bin Samsuairi. For the relativistic momentum, previously, we saw that certain mechanical quantities that describe an event or an object are relative and two examples are time and length. Now, what that basically means is time and length are quantities that are different in different initial reference frame. So, for example, if we have a stationary initial reference frame, let's suppose the Earth, and we have the moving reference frame, let's suppose a spaceship that is moving same very high constant velocity, the length of an object, or the time elapsed for the event within those two initial reference frame will be the difference of that is known as time dilation and length contraction, and these quantities are known as the relativistic quantities. Now, the momentum is yet another relativistic quantity that need to be modified when we are discussing object or reference frame that are moving with a very high velocity. So let's suppose we have an object with a mass m that is traveling with a very high velocity v, and c is the speed of light in the vacuum now. Because the object that has a very high velocity, the momentum of that object given by P, which is also known as the relativistic momentum, is given by the following equation. So m times v given m times v divided by the square root of 1 minus v square divided by c square. So this is known as the relativistic momentum equation. Now, notice if the speed of light c is much greater than velocity of that object. For example, if v is 10 meter per second, then we see that this is ratio inside the radical v square divided by c square is approximately equal to 0. It's equal to a very small number, so we can approximate this to be 0. 1 minus a very small number gives us about a 1, and the square root of 1 is 1. So it will see that if this condition is in fact satisfied, if the velocity of the object is much smaller than the velocity of light in a vacuum c, then p is approximately equal mv divided by 1 or simply and multiplied by v, and this is exactly our linear momentum equation that describes the momentum of macroscopic object that is moving with a very low velocity. So if the velocity of this object is very small, much smaller than c, we can use this equation. But if the velocity of our object is very high, then we must apply the relativistic momentum.
Assalamualaikum, Doctor. My name is Aniq from class AS2513D2. I'm going to represent calculation part of relativistic momentum. So here is the question. Example, inside a television, electron move at speed of 5 times 10 to the power 7 meter per second. If the mass of electron is 9.11 times 10 to the power negative 31 kilogram, find its momentum. So we apply the relativistic momentum equation. P equal to mv divided by square root 1 minus v squared per c squared. Then we substitute the value, which is mass, mass of the object is 9.11 times 10 to the power negative 31 kilogram, and the velocity is 5 times 10 to the power 7 meter per second, and after we calculate, we get the 4.62 times 10 to the power negative 3 kilogram meter per second. Next, if the electron velocity is increased to 0.96 of speed light, find the new momentum. So, as again, we use relativistic momentum equation because the velocity is very high. So, we plot the velocity value and get the new momentum, that is 9.37 times 10 to the power negative 22 kilogram meter per second. Lastly, we go to another example question that relate to the relativistic momentum. The rest mass of an electron is 9.1 times 10 to the power negative 31 kilogram. What is the relativistic mass if its velocity is 0.6 speed of light? If a momentum is to be conserved, the relativistic mass must be constant. With the following equation: m equal to m divided by square root 1 minus v squared per c squared. Given m initial 9.1 times 10 to the power negative 31 kilogram, and the velocity is 0.8 speed of light, then we substitute the value back to the equation and we get the relativistic mass is 1.1375 times 10 to the power negative 30 kilogram. The mass has increased by 67. That's all from me.